Welcome to Neil Shaw Physics. This is the first video in a new series about Maxwell's equations. However, this video will be more math-based because the math is needed to understand Maxwell's equations. If you look on the screen, you'll see that there are 4 equations, but those are only 2 of Maxwell's equations. The reason for that is that the equation on the top left and top right are mathematically equivalent, basically saying the same thing in 2 different ways, and the same thing for the bottom left and the bottom right. There is a reason that these sets of equations are equivalent, and I will explain that. The reason is the divergence integral theorem. Before we start talking about the divergence integral theorem, there's one very important word in this phrase, and it is divergence. To know what exactly is divergence and why is it so important. Divergence is a property of vector fields. A vector field is just a field where every point in space is associated with some vector. One common analogy for vector fields is fluid flow, because you could take the current of the fluid as the vectors. So here I'm going to draw a little rectangle which has some fluid in it, and it is flowing from one location to the other, where one location is like a faucet and the other one is like the drain. However, in the scope of vectors, this faucet and drain have special names. The faucet is referred to as a source, and the drain is referred to as a sink. But what exactly does this have to do with divergence? Well, divergence is a measure of how much something is either a source, a sink, or neither. From an area, it can take the vectors that are pointing in and pointing out, and then produce a scalar quantity that can represent how much of a source or sink or neither it is. A source has positive divergence and a sink has negative divergence. And if it's not a source or a sink, it has 0 divergence. So if you look at what I'm circling right now, you will see that that is where the faucet or source is. If I made a circle enclosing that whole area, you would see that all of the vectors are pointing outwards or out of the circle, meaning that it has positive divergence. Now look up to where the sink is. You'll see if I made a circle around there, all the vectors are going into the circle, meaning it has negative divergence. Then if you look in the middle, you'll see the same number of vectors that are going into the circle are also going out of the circle, which means that it has 0 divergence. In another video, I'll talk about how to calculate the divergence from a vector field. This video is more focused on introducing the topic of divergence and the divergence integral theorem. But before we talk about the theorem, let's look at another example, but using electric charge and electric fields. So I'm going to be drawing a particle with some positive charge. By definition, the electric field lines will be pointing outwards radially from the point charge. So if I draw a circle that encloses the particle, you'll see that all of the vectors for the electric field are pointing outside of the circle. So from inside out. That means that there is positive divergence, or that can be considered a source. Now I'm going to make another area right over here. And as you can see, the vectors that are going into the area are also coming out of the area, which means that it will have zero divergence. I only drew 8 vectors representing the electric field, but if you drew more, the same would apply. And if you notice, every area that you draw that doesn't enclose the particle, it will have zero divergence. That's like one of the reasons why in the first Maxwell's equation, it references the charge of the particles enclosed by an area. So there are actually 2 versions of the divergence theorem. One that relates a line integral to a surface integral, which is the 2D divergence theorem, and then there's the 3D divergence theorem, which is the one I'm going to be showing, which relates a volume integral to a surface integral. So here is the theorem. It relates a volume integral of the divergence of the vector field to the surface integral of the flux of the surface, which I will explain what that really means. So I'm going to draw some cube that we will use to really analyze this equation. Firstly, I'll be looking at the left side of the equation, and then we will move on to the right side. You can see on the left side of the equation, we're integrating with respect to volume, which means that there will be some infinitesimally small volume that we'll be adding infinitely many of. I'm going to draw that really small volume dV now. So before, when we were looking at divergence, we were doing it for typically like larger areas or volumes. Now we're going to shrink that volume down to the size of dV, which is infinitesimally small. And then we're going to find the divergence of it, and then we're going to add up all the divergence from every single small little volume inside of our cube. And that's what the integral does. It can add up a certain quantity of every small little piece of our volume. That's what the left side of the equation means. Now I'm going to move on to the right side, and then I'm going to show why they are similar and why they are equal to each other. The right side of the equation is a surface integral, which means that it doesn't matter about the volume inside of our cube, it just matters about the surface of the cube. So basically, the 6 squares. If you notice, there's a little circle on the integral sign. That basically means that it's a closed surface, which means that it has to encompass a whole volume without any holes. So if this cube was missing a side, it only had 5 sides, it wouldn't be a closed surface. I think it'll be easier to talk about this integral if we show the vectors of f, which, if you didn't know already, f is just the vector field. I drew these vectors randomly. Some are going into the surface, some are coming out of the surface. So if you see on the right side of the equation, we're integrating with respect to a. So there's a dA. So that's an infinitesimally small area. So I'm going to draw that. I'm going to make it big, and then I'm going to make it small, and then move that to the surface of the cube. However, if you look closely, you'll see that dA is actually a vector, not a scalar, which means that we know the magnitude is going to be the area of dA, which is again very small, but what's the direction? The direction is going to be pointing out the surface. So it's going to be perpendicular to the plane of whatever surface it's on. So if we're looking at this cube right here, right, the vector is going to be pointing towards us. So typically you put a dot for that. If it's pointing like into the screen, it would be an X, but since it's pointing out of the screen, it's a dot. And basically f dot dA is like the flux. So flux is measuring how much of something goes through a surface. See that flux is the product of two vectors, and there's a reason for that, and it's the dot product. Let's imagine we have this surface, but we're looking at the side of the surface, so it seems like a line. Now we have some vectors that will be going through the surface. Now you see in this one, the vectors are perpendicular to the plane of the surface, meaning that you'll get the most out of those vectors, you'll get the most flux because it's going perpendicular. However, if you change it and make the vectors so that they're not perpendicular to the surface, you're not getting as much flux because you're not getting as much out of those vectors because they're going in at an angle. And that's why you have the dot product, because when you have a dot product, you multiply the magnitudes of the vectors, but then multiply by the cosine of the angle between the vectors. Now, why is the left side of the equation equal to the right side of the equation? Well, there is a proof for it, and it can be done using Green's theorem, but that's not as important, in my opinion, as the intuition. So imagine that in any volume, it could be sphere, cube, whatever shape you want, all of the vectors are pointing out of the shape, so coming out of the surface. You will see that there's going to be a lot of positive flux because it's going to be pointing outwards. So the dot product is going to be positive because the dA vector is going to be pretty much along the same lines as the vector itself. And you'll also see that if you take the divergence of all the points, that's going to be positive too, because if everything is going out of the surface, there needs to be some sources inside of the volume. So those sources are going to have positive divergence. So when you add up all of the divergence of every single dV, it will be positive. Now imagine the opposite. Imagine that all of the vectors are going into the surface. That means there has to be some sort of sink inside the volume, which means that the divergence is going to be negative. Also, because the vectors are going into the surface, when you dot dA and the vector, it's going to be negative because the angle is going to be 180 degrees, and the cosine of 180 degrees is -1. Now imagine that there are no sinks and no sources, so whatever vector comes into the surface leaves the surface. Now, if you think about it, on one side, there will be a lot of positive flux, because on one side, all the vectors are going to be leaving the surface. But on the opposite side, all the vectors are going to be entering the surface. So the positive flux and the negative flux will cancel out, getting 0. Now, look at the divergence. Because there are no sources and no sinks inside of the volume, the divergence is going to be 0. So now you have an intuition of why or how this equation kind of works. Very useful in Maxwell's equations because it can be used to go from one form to the other. The names of the forms are the differential form and the integral form. Later video, I will show how you can go from one form to the other using the divergence integral theorem. However, there is another theorem that will be used for the other two Maxwell equations. This is the curl integral theorem, also known as Stokes' theorem, and it will relate the curl of the vector field, which is another operation like divergence but measures something different, and we'll relate it to a line integral. That is it for this video. Thank you for watching. I hope you enjoyed. This is the first in a series about Maxwell's equations, and hopefully I can go into a lot more, including applications for each equation and problem solving and using both forms of the equations. So stay tuned for that. This has been Neil Shaw of Physics. Bye.